Dear students, Assalamu alaikum and welcome to our 16th program on Software Engineering 1 course. In the last two programs, we discussed some basic concepts related to software design. I would like to stress that software design is a bridge between analysis and implementation. That is, once we know the user requirements, we need to design the system before it can be implemented. The major design activities that are carried out during the design are shown in this diagram. So during the design, we do the data design, architectural design, interface design, and procedural design. You would like to notice one thing here, that all these designs are obtained from various analysis models that we prepare during the analysis phase. Our today's program will focus on data design and software architecture design. Let's start with data design. During data design, we refine the data models prepared during the analysis phase into implementation-specific representations that can be implemented and processed by a computer. During data design, depending on the nature of software or application you are building, in the data design phase, we design the database architecture and the data structures. You need to design database or data structure or both, depending on, of course, the type of application you are building. It is quite straightforward to transform your ER data model that you produced in the analysis phase into a data model such as a relational model that can be then directly implemented as tables or relations with a relational database package. Of course, if you are using some other kinds of database packages, then the design should map the ER model into that specific data model, such as object-oriented data model, network, or hierarchical data models. Here is an example where we map an ER diagram into relations or tables that can be implemented using a relational database package such as Oracle. So we take a very simple ER diagram as shown in this diagram. We have only three entities: teacher, students, and courses, and some of the relationships are also shown in this diagram. Now, we have very elaborate methods which can be used to transform or map the ER diagram into data model. We used one such method to obtain these tables from the ER diagram. You must note one thing important here in the design, that we basically identified different table names and the attributes which we would like to store in each table, their type, and certain constraints which the table or the attribute must satisfy. So we obtain all these tables from that ER diagram. Of course, this database design is not complete in many respects. For example, we have omitted the detail about many tables and a lot of constraints have not been specified here. But while you are doing the data design, it is important that you must include all the details which are necessary for the implementation. For example, you should specify the internal schema, for example, how these tables should be physically stored on the disk, and all other constraints which should be specified so that the implementer can implement the tables directly into a database package. Also note that information that we use in the data design come from the data model and data description that we prepare during the analysis phase. Now, it's important that once you are doing the design, you should not be including any extra information which is not present in your analysis models. Now, if you come across a situation where you think that some extra information needs to be added during the design phase, that implies only one thing, that your analysis is not complete in some respect. So you should go back to the analysis, improve your analysis, include the missing details, and then come back to the design phase. At the component level, you might need to design the specific data structures that will be processed by that component. For example, if you are writing a CPU scheduler for an operating system, which selects a ready process for dispatch to the CPU, you might need to store the PCB or process control block of the processes you want to schedule in a linked list queue, or in a priority queue, or in a number of queues, depending on the algorithm you choose to implement. For example, if you are implementing first come, first served scheduling algorithm, a linked list queue might be a suitable data structure to be used as shown in this diagram. So this data structure, which defines the structure of the PCB, which includes the process ID and the process parent ID and the other details depending on the operating system. And this is the data structure we define as the struct in C language, and this is the graphical representation of the data structure. So we need to store the head pointer, which points to the first process in the queue, and of course, it is linked to the PCB of the process. Now, while designing the data structure, you should consider what operations are to be performed on the data and how they will be implemented, and then select a data representation that is most efficient for that type of processing. A more detailed discussion on data design can be found in your courses on data structures and database management systems. You should remember that during the data design, we not only design the database as is generally believed, but we also design the data structure which will be processed by the application we are going to develop. The second type of design model that is prepared during design engineering is called the architectural design. Architecture design of a system is concerned with identifying components and their properties and how the components would interact with each other. So basically, during the architecture design, you specify the components or the module which make up the whole system. You identify what functions will be performed by each component, or what functionality will be provided by each component of the system. You should also mention the way these components will interact with each other to achieve the overall performance and the functionality of the software. Architecture design of a software is equivalent to the floor plan of a house, which depicts overall layout of the rooms, their sizes, shapes, and relationship to one another, and the doors and the windows that allow movement into and out of the rooms. That is, it gives an overall view of the house as shown in this diagram. So this is a floor plan of a house. So we show where different rooms and kitchens, doors and windows will be, and how the movement of the people will be from one room to another room. For example, where is the location of the doors and the windows and all other things. So once you have the architectural design of a house, of course, now it's quite straightforward to build a house according to that design. In a similar way, The architecture design of a software is a representation that enables a software engineer to analyze the effectiveness of the design in meeting its stated requirements and analyze the alternatives at a stage when making design changes is still relatively easy. Architecture design is also important for reasons such as it may be used as a focus of discussion by system stakeholders, and it may be reusable across a range of systems. I would like to emphasize the point here that you should not start developing the software unless you have done the design of the software. I have seen many students basically starting their work with the implementation. They straight away go to the implementation and then they do the design while they are doing the implementation. Of course, this technique can be used if you are working on a small system. But for a large system, you will not be able to get a quality software. So keep that thing in your mind, that to develop a high quality software, you should start by analysis, do the design of each and every component you are going to develop, and then do the implementation. Of course, some prototyping might be used, but that prototype should not be taken as the final product. Dear students, the architecture of software affects the performance, of course, its robustness and maintainability of the software. Therefore, particular styles and structures chosen for application not only depend on the functional requirements of the system, but also on the non-functional requirement of the systems. The point is that while you are doing the architecture design, you should not only consider the functional requirements of the system, but you should also look for the non-functional requirements of your system. Software architecture design is a complex undertaking and requires special knowledge, skills, and creativity. Software engineers have proposed a number of architecture styles for different types of systems, which provide us with a framework or template that we can use as an aid to design our system. An awareness of these styles can simplify the problem of designing system architecture. But bear in mind that most large-scale systems are heterogeneous and they do not follow a single architecture style. Therefore, while you are doing the design, you should be looking for what's available, what designs are available, and you might need to customize those architecture design according to your own requirements. But still, familiarity with the common architecture design is a very helpful thing to do your own design. The most commonly used architecture styles are data-centric architecture, client-server architecture, data flow architecture, layered architecture, call and return architecture, and object-oriented architecture. We'll briefly discuss some of these styles. Of course, you can see more details in your textbook. The first style we are going to discuss is called the data-centric architecture or repository model. In the repository model, in the center, we have a data store, a repository, or the blackboard, and various client software or modules interact with the common repository. So in the data-centric style, a data store can be a file or a collection of file or a database, resides at the center of the architecture. And this database is then accessed frequently by other components that add, update, delete, or modify that data. Subsystem components or clients can exchange data in two different ways. First, shared data can be held in a central database or repository and may be accessed by all subsystems. Second, each subsystem maintains its own database and passes data explicitly to other subsystems through message passing mechanism. Of course, the second technique is more suitable if the amount of data that is to be shared is small. But for the large amount of data, having a common repository of data in the middle of the architecture is a suitable technique. The majority of systems that use large amount of data are organized around a shared database or repository. This model is therefore useful for applications where data is generated by one subsystem and used by other subsystems. Example of this type of architecture includes command and control system, management information system or database systems, CAD systems, and case tools. For a language processing system shown in this diagram is based on the data-centric approach. Of course, you don't need to understand how these components really work. The basic idea is that a very common language processing system is built around the architecture, what we've been calling the data-centric approach, where we have the common repository and different components get the data from that common repository. Dear students, the second design style is called a client-server architecture model. This model is suitable for distributed systems. The architecture design of the client-server model looks like as shown in this diagram. We have a number of clients and a number of servers. Clients and server interact with each other with the help of a communication media. The client-server model we just shown you has a number of client and a number of server software. The model has a number of servers which offer services to other subsystems, a set of clients that call on the services offered by the servers, and a network that allows the client to access these services. The clients are generally subsystems in their own right. Therefore, they should be designed accordingly. Similarly, a client is defined as a requester of services, and a server is defined as the provider of the services. Now, there is one misconception. When we use the word server, generally we think server means a hardware, a machine. But we should be clear that when we use the word server and client, we mean the software which provides specific services and the client software which accesses those services. Of course, a single machine can have both client and server software running on them, depending on the software configuration. An example of a client-server architecture design for a film and picture library system is shown in this diagram. So we have various client softwares, client 1, client 2, 3, and 4, and different server software might be running on the same machine or on different machines. The client sends the request to the servers with the help of a network, and the respective server then sends the reply back to the client software. Most internet services are examples of client-server applications, including the World Wide Web, FTP, Telnet, and Gopher. Oracle and many other software also use client-server architecture. For example, in Oracle, we have the Oracle database server running on a machine on which all the data resides, and a number of client software running on the workstations used by the users, and then they send the request to the database server, and the database server then sends the reply or the data required back to the user. The third important architecture design is called data flow architecture or pipe and filter model. This model is applied when input data are to be transformed through a series of computational components into output data, as shown in this diagram. So we have a number of filters, basically which are the data processors. Data processors are connected with each other with the help of pipes. So each filter receives some data, does some kind of processing, and produces the output, which becomes the input to the next filter in the sequence. Of course, the data produced by one filter may be input to more than one filters. When the data produced by one filter is used by only next filter in the sequence, then this type of data flow architecture is called batch sequential. Now this model is quite familiar to you, as we have discussed the data flow diagrams, basically which are the data structure diagrams, basically which follow the data flow architecture. An example of a system based on data flow architecture is shown in this diagram. So we have invoice processing system. There are a number of filters which are connected with the help of pipes. Now each filter receives some data. Now that data may come from some external entity. Then the filter does some kind of processing on the data, produces some output, which becomes the input to the next filter in the architecture. The next filter then processes some data which is received from the previous filter, and it might also receive some new data, and then produces the output which can be used by one or more than one filters in the sequence. And the last filter might produce some kind of output which goes to the user. Dear students, the fourth commonly used architecture style is called a layered architecture, in which a number of different layers, or we sometimes call the abstract machines, are defined. Now each layer provides a set of services used by the layer above it, as shown in this diagram. So this is the layer architecture, where the software has been designed in layers, and each layer uses the services which are provided by the layer just under that layer. Of course, the name of the layers are not important here. You might have different layers depending on the application you are developing. The basic idea is that the software has been developed in a number of layers, where each layer provides some functionality and provides some kind of interface and services which are used by the layer above it. Perhaps the well-known example of this approach are the Unix operating system and OSI reference models, as shown in these diagrams. Here we have the Unix architecture. You can see it has been organized into a number of layers, where each layer provides some services to the layer just above it. Now one thing must be remembered, that each layer provides the services to the layer above it through a well-defined interface. That means once this layer makes use of the services of the layer under it, then the layer makes calls using well-defined interfaces to the layer just below it. Similarly, the OSI reference model has been organized in a similar way, as shown in this diagram. So we have again 7 layers. which is the OSI reference model. Of course, different layers provide different functionality to the layers just above it. Then each layer uses the services of the layer below it by making well-defined calls to the layer below it. Dear students, the last architecture model we would like to mention is call and return model. A general call and return model is shown in this diagram. We have a main program and a number of routines or functions organized in a tree-like structure. Main program makes calls to routine 1, routine 2, and routine 3, and then the routine 1 makes calls to routine 1.1, routine 1.2, and so on. Now, the call and return model is, of course, the very commonly used architecture style we use when we write simple programs. When a module makes a call to the another module, we know that the module has to pass some information to the called module, and consequently, the called module might return some of the results back to the calling program. Now, there are two different ways in which this can be achieved. Either the calling program sends the parameters to the called program, and then the called program does the processing or performs the action and then might return some result back to the calling program. In a distributed fashion, a calling program might call a function which might be residing on a different machine. That's what we call the remote procedure calls. Both methods are used and they follow the call and return architecture model. Dear students, in today's program we discussed data design. We also discussed software architecture design and briefly touched upon some of the common architecture styles. In the next program, we'll talk about software testing, different techniques and methods which are used to test the software. Till then, Allah Hafiz.